Hello everybody, welcome to another stream. There we go. Glorious sir, thank you so much for that sub, really appreciate it. How are you doing? How are you? I love that Bournemouth salute. So last stream... Oh, and also by the way, there's a new Nick Johnson album. So I want to play that one after this one's finished. I think it'll be good. Because I haven't heard it yet. It's 4 months old. So that's what I mean by new. But yeah, we got this tree. This tree is debug visualized on the CPU, but it also runs on the GPU now. So today's objective is to finish it off, get it packed into these packed nodes. So we'll go over what it's in this sort of temporary build node state. So it's a bit wider, and we want to pack it down so it's super nice and cache efficient to traverse, and then actually traverse the tree as well, and hopefully render more than just this sphere that you're seeing, or ellipsoid that you're seeing here. We should be seeing multiple today. That's the objective. So let's go and investigate. So first of all, I think memory serves that I made an array a little bit too small. Yeah, the build nodes actually needs the number of leaf nodes. Yeah, I didn't... The build nodes, this is the array of nodes while we're building, so they're a bit wider. We actually need to have internal nodes capacity plus leaf nodes capacity worth. I remembered that from end of last stream. So our build node is currently a parent index, a visit count, children count, and children indices. So it starts off as a binary tree, then we turn it into a quad tree. So we've got those two steps working. We just need to then pack it into this lovely node here. But I was doing some thinking off stream, and what I've come to is we haven't got enough resolution. So what I mean by that is I'm thinking of doing like an RPG where there's kind of top down. There's probably going to be tiles, but obviously it's going to be 3 dimensions or whatever. So it's going to cross that way, and down the X and down the Z, and then the Y would be like that. For crying out loud. How will it make dimensions look good? This makes it look isometric, though, but it won't be isometric. But yeah. So the idea is if you have put it this way, we're only using 10 bits of resolution to place this node in world space. Well, it doesn't have to be in world space. It could be kind of in view space. That could be fine. But the point is you only have 10 bits of resolution, which is 1024, which is the maximum value. So we go across the x-axis. Like, obviously the positional data will be higher resolution when it comes to game logic, but when we could try and render it, it's going to be it's going to snap. Or it's going to jump between, it's not going to look smooth. So I think we need more resolution on these guys. So we're going to actually redesign this, and then we'll pack it. Because we've got some unused bits, and we need some more resolution. So the basic idea is we have a BVH node which is 16 bytes. And we have at most 4 siblings, or 4 children of a node, right? So basically, you fit 4 nodes in a cache line. Quite cool. So we should be able to iterate over all of them and do our intersection checks. And it shouldn't have to wait on accessing memory as much, right? That's the idea. So we've got to keep this 16 bytes. So we're going to have to sacrifice some precision from these here, this final word here. So we've got 128 bits. So that's what we're gonna. Wait, is that right? Wait, how many bits have we got actually? Times 4, isn't it? Right, so it's 64. No, it's times 8. Yeah, 128 bits. That's what we got. So we're gonna work out how we're gonna fill 128 bits, and then we'll worry out how do we fit it into the words. Can't say I followed much with BVH, but it's exciting to see it come together. Doing fine. Got sound mixing up and running. Now trying to SIMDize it. Awesome. Yeah, that's something I need to look into at some point. I'm interested in learning it. Yeah, I've heard people do a lot of SIMD optimization with audio. Pretty clever stuff. There's just too much stuff in game engine programming that I just want to do, you know. All sounds fun. But yeah, it's cool. Like the first couple of episodes we're still figuring out like how are we doing the construction. And it's really just started to come together now, which is great. Well, it came together like a couple episodes where we finished it on CPU side, doing a debug visualization. And now, yeah, it's building on GPU, which is great. So we're just doing the packing now. So it's going to be cool. It's going to be cool. Hi, Chandu. How's it going? How you been? Sure, too much. Yeah. I'm not super into my physics yet. But whenever I obviously need proper physics in a game, I always write it from scratch. And try and learn stuff. Obviously this game won't need physics. Although Mixer is a glorified summonator. Right. Yes, he's just summoning a bunch of sounds on top of each other. Amazing. You're good. Not giving up on restoration yet. I'll keep you posted on that one. Sweet. That's cool, man. Yeah, keep it up. You got this. Make that triangle. Make that triangle. So we've got 128 bits, right? What can't we change? So I think the rotation is great, right? We've got... Wait. 10 bits per component. Ooh. Okay, yeah. We're going to move that down to 8 bits per component. So I think we're going to do... I think we'll have 24 bits for the quaternion. For the rotation. So how do we do that? Well, it's the XYZ of quaternion, and the W is implicit because XYZ and W all add up to 1, positive 1, right? So it just means that to get W, you just need XYZ, and you can just do one take, the sum of XYZ, right? And voila. So we can infer that, which is fine. So we're going to do 8 bits of precision per channel or per component. That's 24 bits. So what's the lowest we can go with on this? So this one is saying based on the node type. See, this is a bit... It links to a child BVH node. Oh yeah, this is cool. So basically, what's the maximum number of nodes we're going to have in a BVH? Well, assuming you need... well, I think it's divide by... It's round up, divide by 3, isn't it? Take 1 or something like that. I forget the logic. But yeah, say if you have... Yeah, say if we're going to have like... We're definitely more than 16 bits. So if we did 18 bits, that's 256. Maybe we could do 18 bits? I don't know, maybe we won't need more than 16 bits. Why don't we just start off with 16 bits? You know what, if we just did 20 bits, then that's a mil, right? I've run it up. Yeah, we just support a million nodes. So that's not really a million ellipsoids in a model. It will be, yeah, it would be something like a bit less than that. But I think that can't possibly want more than that. We probably want less actually, like far less than that. But let's just use that number. Let's just say we use 20 bits for the so that means we can have a million materials loaded. We can have a million BVHs in the scene. So that's what this, because this is a union basically. So if we just say 20 bits for that index, for that star index, right? So that's already 44 bits. So now the remaining bits that we have is for the half dimensions and the position in either view space or local space. I think we'll be doing. So we have 84 bits left. So I think we're currently doing 10 bits. So 10 bits of precision is going to get us 1024 like different values. But again, if you take the screen resolution in as an example, we're going to have like you know, if we have a 1080p screen, which is basically 1920 across, you're clearly going to see an object move and it's going to stutter across the screen. So that's probably not ideal, right? So we definitely need more than... So if we did 16 bits, we get 64. 64K. So, you know, it's kind of nice. And I think we only need good resolution on the X and the Z axis. The Y axis could suffer a little bit. And maybe the Z axis could maybe have half, could maybe have a little bit less as well, because if we're doing a camera from behind, you definitely have a I've got the game running now. Yeah, I can't really. Yeah, so maybe you're gonna have the camera like that. You're gonna have your models going. Do something like this. You have your models and that going across here. Well, it's the x-axis, right? The z-axis is going off into the distance, and the y goes up. It might be looking more down like that. I'm not sure. The camera. So I think, yeah, the x needs the most precision. Z is the next amount of precision, and the y is the least. Right, so that's a little trick we can employ there. So we could probably say so if you did 16 times 3, because there's 3 axes, right? That's going to get you, was it 48? Yeah. So we only have 80, whatever left, isn't it? 84 left. So that's kind of close. And then we need, the last thing we need is this half dims. So the beauty of it being half dimensions is that it is, it's definitely 1 bit less than the positional data. Because positional data needs to access, imagine this is the bounding box that that you can address. The positional data needs to address everywhere within here. Whereas a half dimensions only needs to address half of the space, right? It's as if you come is that true? Is that true? Because what happens if you go outside the bounding box? Say if you're here and you have something that's absolutely massive in size. Or whatever, I don't know. Could that... Yeah, that would be illegal, basically. Yeah, so half dims can have 1 less bit, so it's 15 bits. So that's 45. So plus 45, 93. So we're already some bits over. We had up to 84 bits. Because we did 128 bits, take away this 20. We're using for that, and 24 we're using for rotation. So we overshot by 9 bits. So we've got to make up 9 bits across 6 components. Oh shoot, there's 2 bits for a node type as well. Crap. Yeah. Alright. So we're even less bits then. We've got 82 bits. So we're overshot by 11 bits. So again, the next thing we can say is we need 1 less bit for Y, for Z, and 2 less bits for Y. So that could get us some savings. So say if we needed 15 bits for Y. So 16 plus 15 plus 14. That's 45, right? So that's as if we did 15 times 3. Then imagine if we did the same thing here for this half dims, where we said we need 15 bits for X, 14 bits for... Wait, 15 bits for X, 14 bits for Z, 13 bits for Y, 42. So we had 45, 87. So we saved 6 bits there from 93, but we still want to go to 82. So we can still employ that trick some more. And I think the Y-axis, we need far less precision. I think we can get away with shaving 2 more bits off that. So I think let's just say we're going to do 16 bits for center position X. I don't know what anyway. 15 bits for center position Z. And so it was in 14, but let's take 2 more off and let's do 12. And that's for Y. So then we do the half dims. So take 1 down for the half dims. Half dim X, Y. So we add all these up. What we're hoping for is 128 bits. So let's see. We'll probably just be off a bit. So it's where you need Excel or something, 1 bit. Right, so I'm 1 bit over. So I could just take it from this, because realistically I'm not going to actually need... You know what? Let's make let's actually take some bits from this index, because that's 1,000,000 nodes. I'm not going to need 1,000,000 nodes. And having different precisions for these is just a bit... Well, it could be fine. What should I do? Should I take away... So we did 18 bits. That's 256 K number of nodes. Most. And that's 256,000 different BVHs. I don't think we're going to need more than that. And 256,000 materials. Should be fine. You know, I'll just take one bit off and we'll just call it that. We can faff around with this more in the future. For now, we just need something to work. So we can always see what it's like and tune it, because then we're working with something that's real rather than just trying to imagine what will be real. So right now we just got to pack it in these words and then change the packing code here. We're using fixed point for a lot of things. Wait, are we using fixed point? No, yeah, we stopped using fixed point because we can just encode it in as... Yeah. Right. Alright, this is good, this is good. So how are we gonna pack this in? So we've got 32-bit words, and we've just got to find places for these. So we've got to arrange them into, or hopefully fit them nicely. If not, they've got to spread across a couple of... No, they got to spread across word boundaries, which kind of sucks. So we need to arrange these nicely. So we do 16 plus 12 plus 50. Oh, sorry. What I tried to do then. Definitely going to go overboard there. So that's 28. Yeah, so we've got a bunch of... Okay, so we've got a bunch of these where as soon as you pair them up, they're basically filling up a word. Oh, wait a minute. Did I miscalculate my number of bits that I have? Shoot. No, that's just right here. 32, 64, 96. Yeah, okay, so that's fine. So basically you can fit pairs of these sort of like 16-ish ones in. So how many pairs? So we should have so 1, 2, 3, 4, 5, 6. That already. But then there's this 19 one and this 24 one. These are quite high. So let's get this 19 one and see what we can do with it. Now let's copy this. Nah, alright. Right, so these are the numbers. So our 19 one, what can we pack in here to get it? Is there a number that fits perfectly snug with this? So we need 13. Well, we ain't got a 13, but we've got a 12. And we've got a... Or I could make it such that this is 20. No. Yeah, whatever way we cut it is gonna be a bit odd. So this is gonna be 31 bits. So that's one word already. It would be nice if we could just tack that in there, but we can't. But let's take the next one, which is 24, right? So if we had 8 bits that would get us in another one, but actually, sorry, we should split this up into a bunch of 8-bit ones. Because this doesn't come as a 24-bit thing, right? Oh, who's this dude? GPU viewers, wow. Amazing. So this has broken the problem down a lot better. Right. We'll think about this one in a bit. Yeah, so obviously, right, if we take this 16 one, that fits into a word perfectly. So you take these two 15s, that fits this node type into a word perfectly. And then what you're left with is this. So this is missing 1 bit. These are missing, these are obviously over by 1 bit, right? If the maths works out. So that'd be 22, and these are 11, so 33. So this is where we can, I don't know, what can we do? I could probably decrease the resolution of that, dims y, and then increase the this index, and that will balance it out. Yeah, I think that this is good enough. It fits us in. It really has skewed things all over the place though. So how can I orientate this such that can I reorder it so the things that make up a component, that make up a vector or something, are in the same ones, the same words? It's a bit weird, isn't it? So, yeah, so something that I'm missing from this as well is that if it's a bottom level leaf node, oh no, sorry, this is okay, it is the ellipsoid. So you'll be able to, yeah. Sorry, I was thinking for a minute like, oh, I don't have I need a reference to the ellipsoid, but the node is the ellipsoid, so it's fine. Yeah, so I referenced the material, which is that index thing here. Yeah, I guess we can always shuffle it around later. I'm not. If it becomes a problem, like we can always, yeah, look at it later. So I guess let's make this the new documentation. So my first word is this. Maybe we'll shuffle the words around, but yeah. So to get the center position, it's a bit of a faff. But at the end of the day, we probably want to get all the components out into local variables kind of at the same time. So I don't think it's too bad than being spread along different words, I hope. I don't know. Right, this is good. I like it. Yeah, so we got 20 bits there for that thing. Sweet. So let's go ahead and change the quantization code. So the center position comes in as a signed norm value, and then we have an unsigned norm value for the dims. So I just got to work out when we pack. So we want to get the center position X, Y, Z. The X resolution is 16, so that's 60. What's the max number? It's 65535, isn't it? Yeah. So then resolution for that is 12 bits. Right, 495, because it's one take of that result. Sorry, that was for the, yeah. Then 15 bits, so it's 35767. Let me double check that. Yeah, so 32768, but let's take one. That's the max number. Neat. Right, so that's bringing that down there. Half dims, 15 bits. The X, it's that value there. Y, which is half dim Y. 10 bits. We all know that one. 1023. And then half dim for the, where is it? For the Z. 14 bits. Right, 16383. Voila. So after we've got these quantizing correctly, we'll pack them in correct because we obviously messed that up there. So rotation, these have changed to be an 8 bits, so it's 255 precision. All right. Cool. So let's go ahead and figure out how we're going to do all the packing now. So the first word, so let's get all the quantizing done here. And then we'll just pack it in. So the aim is to, so 10 bits for, so in this one, so it's half dim. Right, dim Y. Dim Z. And then rotation Z. So that'll be how many bits? So 10 and plus 14, 24. And voila. So the next one is center position Z, half dim X, and then the type, the node type. So if we were to sort these out, that is 15 bits, and then add 15, so that's 30 bits. Cool. Word 2. So we need center position X, rotation X and Y, and then What else are we figuring out? Right, 16 bits is the offset plus another 8, so that's 24. Nice. Final one. We need center position Y in there. So center position Y. And there we go. So that's the packing when it comes to initializing this node. The remaining thing is to unpack. So we've got a bunch of these lovely functions here which help us initialize, take from the, taking some arguments as floating point and just turn them into this packed node, which we'll be using in a bit. Then we've got this way of extracting these things out. So the node type is now in word 1. I need to shift 30. So we need to get that same sort of logic here. Just need to get the numbers updated. So 65535 here. Then it's that one and that one. The precision does vary a lot for the y-axis. Yeah, so how are we unpacking these? So that's in word 2 at the start. Then, wait, we didn't AND the bits out? That ain't gonna work, is it? So you need to AND 2 bits, that's 3. You need to AND... Well, at least we managed to catch this problem by redoing this. You need to AND some form of bits. We'll figure that one out. But yeah, that was weird. So how many bits we got? We need 16 bits. That's 4 Fs. What do we need here? So you come from, the Y comes from word 3. You're at the start as well. You need, it was 10 bits, wasn't it? So that is, and then a 3. Right, 3 is 2 at the start. Then 8. Now the other one is word 1 at the start as well. So that'll be 14 bits. Wait, 13. 15 bits. So it's, let's see, E. There we go. Nice. Voila. So we get rid of that now. Cool. So we're just going to go ahead and unpack half dims, rotation, and then these guys, and then we can get back into calling these, packing these nodes. Right, so these need that same sort of change where we make sure that we extract the only the certain bits that we want. If not, all hell is going to let loose. Alright. So where are we getting these guys from? It's a good question. So word 1 is for X. Right, word 0 is for Y and Z. So that is after 15 bits. I think it was 15 bits. Yeah, 15 bits, the X is there. 0, then 10. Right, so this is 15 bits worth. So that's EFFF. This one is how many bits worth again? 10 bits, so it's 3FF. And this final one is that 12 bits? What do we agree on? 14 bits. Right, so 14 bits. Three. Yeah, so you got 4, 8, 12 plus 2, which is 14. Sweet. Yeah, that's looking good. So rotation, this one is all the same. Very easy, 255. Right, it's got 8 bits per one here. Then we imply the W coordinate for the quaternion. So how does one... Yeah, I'm just making sure they're converted from sine norm correctly. That's all right. Yeah, so how does one do the... yeah, where are these packed, right? They're packed in, right, word 2, x and y, and then word 0 for the z. Right. So it's 8... Wait, where's word 2? Right, so this one's at 16, and the other one's at 24. We should be doing that same thing that we did before. Well, we do, and... So when it comes to move 16, move 24, right? What is this one? Move 24 again, obviously. Yeah. Nice. So that should be all the complicated ones done. These are simple. These are just shift right 20. On word 3. Because they're all just that ref index. Okay, that's also be good. So now we have our new packed node. It's a lot more skewed now. So everything's just all in different places, but it should be okay. We can monkey around with it more later. But yeah, at least it's all packed properly now, and the resolution should be sorted out, so things shouldn't be jumpy. Right, so let's get back to the actual shader code. So we build this quad tree. So in the form of this, I'm giving it a run again. In the form of, we build a tree like this, right, where it has a potential of having 4 siblings or 4 children per node. So this is what is being built on GPU right now. So that's great. But the issue is that it's in the build as a BVH build node. It's not as that BVH node, which is the packed version, which should be better for ray tracing against because it should be more cache friendly. So the idea is that we want to make this packed BVH node. So one thing is that there's a bit of a thing where a BVH tree has a very unique thing about it, and that is node 0, right? It always has 1 node. It doesn't have any siblings. So I could waste I could waste node 0, and it has 4 siblings after it, but I'm thinking that we don't need it. So, and the reason is because if you have a bottom level BVH which references a model, that model should have already been hit in the top level BVH anyway, so node 0 is not going to be, it's going to be useless. So I'm thinking we just get rid of it. So that's one thing about it. Yeah, so we have to figure out yeah, so where's the I don't think we've made the buffer yet. Right, I didn't call this buffer ID at the end. That is a big mistake. So we're going from those build nodes, and we're going to turn them into... Okay, so we're going to have another one which is going to be the actual BVH nodes. These are going to be persistent in memory. And we're probably going to have to defrag these things in the future. But the defragging process should be as simple as marking the memory as deleted and recopying it from CPU. So I think in future that is going to be a quite simple process, and we should be able to keep stuff quite packed in the one big nodes buffer. I think it should be fine. So this, let's allocate it, is going to be a lovely packed node. So this one is going to be BVH node. And I think right, so those are the maximum number of leaves in a BVH. So I said we're gonna have 64k leaves. So maybe that index is a bit overkill, to be honest. We allowed for 1 million. We probably want more than 64,000. Yeah. That's alright though. We can faff about with it later. So what else we'll look into? So that's when you, per BVH, what's the most number of leaves? So now we need to probably have another one where it's like, what's the most number of instances, right? And again, we'll probably say 64,000. So, I don't know. What is, yeah, that'd be 4 billion, wouldn't it? Yeah, so that'd be 4 billion. So I'd be instantly allocating 4 gigabytes. Probably not a good idea. So if we half that, and make that 3,768, that's 2 gigabytes of memory. So we half that again. That'd be 1 gigabyte. Then we half it again. So 16k would be 1 gig. Then 8k would be... So we stick with 8k for now, but we should tune these numbers. So that'd be 512 megabytes pre-allocated just for BVHs. So yeah, we only render BVHs anyway, so should be alright. So we're gonna go ahead and try that. So this is the build. Build internal nodes, build. So this is the actual overall internal node capacity. Wait, what did I do? Number of leaves, number of... So the overall you multiply this by the number of instances. So we should probably say for a single BVH. Then this one is going to say, well, what's the maximum number of instances we're going to have? And so this is total. Hey, Sturdy Pose, how you doing? How are you? And there we go, that's the maximum number. So that would be all of our nodes being allocated, or a whole buffer for all of our nodes to be sub-allocated from. Right, I did say there's a new a newish Nick Johnson album, so we're going to put that on. It's 4 months old, but I want to hear it. So, right, with this, we're going to be bump allocating it to begin with. In the future, we can do some more intelligent allocation scheme. Well, in future, I mean when we do top level BVHs, which is going to be after bottom level is rendering. So this is cool. Now maybe we can bump allocate. Doing great. How you feeling? Yeah, not bad, not bad. I was super tired yesterday. After work, went to a shop, and then we came back from the shop. I usually get some free time on a Monday to exercise, but I just crashed down the sofa and went for a snooze while my wife cooked a lovely meal. So, yeah, I was super tired, but I'm feeling much better today. Been super busy and just not really sleeping too much. I think I caught up a bit. So, right, I think it's now time that we build that shader. So it's the BVH pack quad tree shader. So how's it going to work? Big questions. Simple answer. So like the previous algorithm, we start off all of our threads on the leaf nodes, right? Every thread gets a leaf node and it runs, they can be running kind of at the same time and some might run a bit after. But the idea is you go up from the leaf node and you go to your parent and you increment a visit count, right? And when the visit count is not equal to children count, the thread terminates. When it equals children count, it carries on up the tree and it repeats. So what we've just built then is a bottom up traversal, highly parallel algorithm, right? We've already implemented it. That's how our quad tree construction worked from a binary tree, right? Took the binary tree, crawled up the binary tree and split nodes into, or joined nodes into bigger quad nodes, right? So we're going to get that part of it. At the same time, we are going to, what we're going to do at the same time? At the same time, we're going to get all of the children and pack it into that. Yes, I think we want to reserve. You get all the children, pack it in. Yeah, what does the thing? Yeah, when you reach a parent, the parent's the one which packs the children in. Yes. So when you reach node 0, node 0's got a special place, and that is at the start of the yeah. So the start of the allocation is where the right. So why don't we there's a thing. I like my things. There's a thing where here it is, BVH next node index. So this is going to be our thing we bump allocate with. we're going to initialize this to 4. So this means that 0 to 4 is going to be where all the children nodes, the root children nodes go. That way we can just have a pointer there, and then it just, whenever we reference the BVH, we can reference the start of the nodes, and then everything just is after that, which would be super nice. That'd be cool. So yeah, how do we do that traversal thing? How do we get started on it? That is the build quad tree has all the answers. So we're just going to copy all the answers into the function and go full ham. Yeah, staying on top of exercise routine can be hard when you're busy and sleeping sucks, but at least you're feeling better today. Wife contracted whooping cough, right? And now I need to sit. I also need to sit on my butt. No. Yeah. Hard to not catch colds when your wife's got one, isn't it? You know, because you want to be all lovey, and then like, you know, too late you got the cold. But yeah, I don't know. I was really good. I had my exercise routine down, but for some reason it's just not been going the past week or two. There's been an accumulation of no sleep, I think, which kind of sucks, but I will build it back. It also around summertime, not gonna lie, when the temperature gets a bit warm, I get more and more lazy. Things are just too, I can't deal with heat. You know, I'm British, you know, so I complain when it rises above a certain threshold. It's the way we do it, you know. Too cold, too hot. But yeah. So we get all the leaf nodes. Oh yeah. So we need to, let's figure out, get the data in. What data we need? So we're going to rewrite to the build nodes. Number of leaf nodes, we need that. We also kind of need like, where are these BVH nodes going to go? What's the allocated start index? Right, and also what we kind of need to know is like, we need to know from the build quad tree. Well, we already know this based on the number of nodes. The number of leaf nodes, you can work out the number of nodes you need to allocate. Yeah, this is fine. So we can always build a custom allocator shader in between these two. This is fine. So this is pretty good. So we're gonna get the number of internal nodes. How does this make sense? Yeah, this is for the build nodes. Build internal nodes count, build node index, shall we say. So we're going to go ahead and monkey around with this. So we don't need to reset it here in the future anymore. Does visit, yeah, it does get initialized to 0. All of this is unique to, so this is just the loop which does the traversal up the tree that I was just talking about a second ago. But it needs to be modified for a quad tree now. So here's how we do it. So we've got our build node index. We start at a leaf node. So we fetch the leaf node's parent. Then we say it's not equal to null, basically, or invalid. We go up, we atomically add to the visit count. And then when the visit count is not equal to 4, we are not the last child node between our other sibling to reach the parent. We can just simplify that. We are not the last child node to reach the parent. Screw it, let's put that in. We're not the last child between our siblings to reach the parent. Terminate here. The other sibling, the final sibling, will be allowed to traverse up the tree. Final sibling goes here and then goes back up, right? So that is pretty sweet. So now this is where the fun begins. We have to go, so we want to bump allocate. This will be what's known as our node. Oh, shoot. This will be what's known as our destination node index, and we're going to bump allocate it using the atomic add U32. And we're going to add for that BVH next node index, and we're going to add 1 obviously, and shabam. So this is going to get us we're going to add 4 as well, because we want to allocate 4 children in a row. So we should now be able to start taking those children. Where is it? Here. And constructing our tree. So I've just thought about something. And each build node doesn't even have an ellipse. But we are starting from the... I should have put an ellipse in here, right? So we put an ellipse in the build node. It could go in, so it can't go in here, but when it traverses from the bottom up, it could build the ellipses. But equally, it would just be kind of a waste going in there anyway. So as part of the quad tree, we could get the ellipses from, or the ellipsoids from the leaf node. See, we haven't even got the ellipsoids on the GPU yet. So yeah, they've got to be put into they've got to be put into sine norm and unorm space. So we could probably make another buffer for those. So next we've got those Morton codes. What we need to have is another buffer, and this is going to be the leaf node ellipsoids, or we could just call it ellipsoids. And this is a parallel array with the Morton codes. So the Morton codes are just used. Thankfully, there's a sorting. We've got our sort function supports a payload. But the payload is just another 32-bit in, isn't it? So the AMD parallel sort that we implemented, it only supports having a the payload be an index. Right, so you have terrible, like, unless you could pack an ellipsoid into 32 bits, it isn't going to be that. It's not going to be, yeah, the access pan's going to be horrible. But it is only when you're building the tree, and I think ellipsoid. I think when you build the bottom level BVHs, it's going to be done in the editor anyway. And the top level won't have this problem, I don't think. Maybe, it might have a similar problem. Yeah, won't really have this problem. Yeah, you're not packing an ellipsoid into 32 bits. So I think we're going to have an ellipsoid indices buffer as well. It's horrible, but we've got to do it. So, right, let's chuck these in. And we can always improve it later, I guess. So an ellipsoid indices buffer, ellipsoid indices buffer. That's just based on the number of leaf nodes. Yes, U32, right? Then we need ellipsoids buffer, which has. See, I don't. Did we make an ellipsoid in the end? I don't think we did. Right, so we'll just define this as a big old. So there's a BVH build ellipsoid. So obviously when you're building it. So we'll just build it, make it a big old. Center position has to be unorm. Right, so -1 to 1. And then half dims. Wait, sorry. Snorm, -1 or 1. And then unorm 0 to 1. Do we need anything else? Well, we also should really probably have a material index for that. Yeah, you need the material index. I think that's it. So here we go. So the build node, or the BVH build ellipsoid, goes in here. So they're initialized now. So yeah, so we sort the Morton code buffer. So what we need to do is also sort. Wait a minute. So we upload. Right, we should make this data more proper. Let's just get a bunch of ellipsoids. I don't know how I want to do this, to be honest. Can I say BVH build ellipsoid? Yeah, we could do a rand, do a seed, a bit of a fixed seed and a rand between 0 and -1 and 1 and stuff like that. But we'll get overlapping though, which kind of sucks. Yeah, we should keep them all about the same size, but just randomize it a bit. So maybe we'll do like, hey, we've got 32 of them. We can maybe even go higher. Let's just go, 228. So we'll do a for loop over all the Yes, this copied the ones from the test code. We'll change that. So for all the ellipsoids, I would like to set center position dot x equal to rand, and then you want to so turn into float 64, divided by rand max. So I get you 0 to 1, but we need to be -1 or 1, so we times 2 take 1. Now you obviously want to do that for every one of these, and I think we're doing a fixed seed because we did srand. Yeah, cool. So if we now do the same thing for half-dim, but we obviously drop that, says 0 to 1. Then we also want to set material index to something, but we obviously need to do that later. Because we have material support. We have support for PBR, but we don't really have materials yet. Yeah, they will come. But as soon as we have a model, we can build that in. So the next thing to do is actually put in some Morton codes. It's quite easy to do that. So we get some more codes in there, then DST Morton codes, DST ellipsoids. What's the number of Morton codes? Good question. BVH ellipsoids count. Sort that all out in just a sec. So do 128. So the next thing is we need to now go over all the ellipsoids and basically do a mem copy, but so this will upload it to the GPU into that buffer. But we also, I have to change this, BVH, there we go. But we also need to sort out the problem with the But we also need to solve the problem with the Morton codes. They need to be updated too. So the Morton codes, they need to. So I think I've got the function for it somewhere. Where's my boy? I might not have it in this code base. Let me fish it out of the old graphics one. Right, it's not in that one. Right here we're more than 3D to 30 bits. So this packs it from a 3D coordinate into a 30-bit int. So we're just gonna get this, and we're gonna go ahead and move it into the shed. There is a BVH section apparently. Right, so expands more and expand bits. Yes, so for those of you who aren't familiar with what a Morton code is basically this, right? You take a 3D coordinate, so imagine this is 2, 2, or this would be 1, 1, right? 0, 0, 1, 1, or if you're bottom lefter, it's different. But yeah, imagine it's 1, 1 from here as an example. Actually, this starts from bottom left, so yeah, we'll start from bottom left. So imagine it's a 1, 2, right? So 1 along the x, 2 up here. So you're converting it to a 3D coordinate, or 2D coordinate in this case, to a 1D coordinate. So this is actually 0, 1, 2, 3, 4, 5, 6. So it basically like spreads the bits out and then ORs them together, right? It's pretty clever, and it produces the Z curve. So things that are near each other in the 1D space are end up being near each other in 3D space. Kinda. Because you can get these big old jumps. When it ends a sequence, it can do a big old jump like this. And as the Zs get more and more macro, so there's a micro Z like that, another one, another one, another one. When you've made 4 micro Zs, you get a macro Z like that. So it ends up starting here again, doing 4 micro Zs, and then making another macro Z, following the Z pattern, dun, 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 dun. So it produces 4 like that, right? And then you make another one up here, and then, yeah, down there. And so it just, yeah, that's Morton codes. They're pretty cool. So you can get a big old leap all the way from up there all the way to down there just from one index. So they're kind of close most of the time, but they're not always. So yeah, we're taking that 3D coordinate into, so we're just going to say so we'll say give it to us between 0 and 1, but yes, and then we then have to do the multiply. And I'll clamp it like a chimp. Get out of here with that C. Ooh, science. Cool. Very nice. So I like that a lot. Let's go ahead and start using it. So we've got to be careful, make sure it's between 0 and 1. And if we take a look at our ellipsoid center position, it is actually -1 to 1. So we need to do the mol s by 2, and then sub s by 1. I should already have a function which just converts from unorm to sin norm. It would be much more, it'll probably be better. So why don't we actually just make that now? I could put it in GPU, I guess. I don't know. I should probably have it in my maths library. Be pretty sweet. You know what, I won't bother doing it. I'll just live with the pain for now. So this will upload those Morton codes. And everything should, we should now have an ellipsoids buffer. But yes, the next thing we need to do is properly sort it. I guess, should we just check and make sure it doesn't crash and burn? It should still be fine. Right, let's go. Oh, I got a Vulkan error. No. But the size of the heap is actually only this big. The Vulkan spec states that. What have I done wrong? Did I just allocate too much memory? Now the question is, did I allocate too much overall, or just one of them is like extremely big? That looks big, doesn't it? I think we've got ourselves a problemo in one call. So we're going to put a breakpoint here. Wait, we know which one it is, right? 197. This boy, apparently. Did I try and allocate 512 megs from something? Oh wait, 512 megs times by 16. Right. There's not 512 megs when you... Yeah, so when I... shoot. I forgot it's going to times it by size of node. Yeah, so obviously we have 512 megabytes times by 16. That produces 8 gigs. 8 gigabytes. Because that's 16 bytes per node. Right, we'll make the numbers go down a bit. Should we bring this down to 16? 384. So we do some quick maths. Maths. Right, times by 16. 2 gigabytes. Still way too many. So that'd be 1 gigabyte. Right, let's give that a go. Probably more than a gig actually, but yeah, that should be alright. Might be 2 gigs. Right, okay, we're running. This is good. So we've now uploaded the ellipsoids that we want to render in the scene. So now we need to make sure that they get sorted. Oh, we didn't put the indices in, did we? We've got to do that. So there's another one called ellipsoid indices. That's another buffer that we made. So when we build a BVH, we have to unfortunately make an ellipsoid indices one, and the reason is because our highly parallel sorting code, courtesy of AMD, has a payload option, and the payload option only supports a 32-bit value. So we can't pack an ellipsoid in there, so we have to have some indices. So simple as that. We just assign the index in there. But we've got to be careful and do the sort. So the sort is sort with payload. Can be good. And it takes in a payload buffer as a second argument. So we need to supply that here. gfx.bvh ellipsoid indices buffer, like so. So that should now sort the Morton codes and then sort the... And while it's on the Morton codes, it sorts the ellipsoids as well. Rightio. Very good. So let's take a gander. Right. So now we have the ellipsoids, the ellipsoid indices. Now we have all of the data ready to actually start building this packing the quad tree properly. So I need to find out where's this pack quad. Here we go. So we need to put these buffers in here. So we need a read-only buffer on the ellipsoids. So these are the leaf build ellipsoids. Right, this is indexed with the leaf node index. We only get it on the leaf nodes. And then we can start passing it up the tree, and it's going to be amazing. What else? we also need the indices. Yeah, sorry. So the indices get indexed with the leaf node index, and then you get the index, and that goes into the... It's a redirection table, right? Okay, so now let's finally get back to that shader where we finish the packing code. So, right. So quick recap. The way the shader's working is we're simply starting off at the leaf nodes. The leaf nodes go up to the parent, they increment a visit count. When the visit count is equal to the number of children, right, that's the bug. I've not done that. Yeah, when it's equal to the number of children, then that thread is the thread that lives and carries on up to the parent. The rest of the children get terminated. And if you repeat that, you'll be able to traverse up the whole tree, multi-threaded. So that's all this code here does. So I'm going to be careful. Yeah. So here, we get here if we're the thread which is the last child to come through. So we allocate 4 nodes. And now this is where I needed the ellipsoids. So we need to go over all the children, get their indices, have a look, and figure out... Do I need... I'm trying to think, do I need a scratch buffer to get some... Yeah, I'm wondering if I need a scratch buffer to put the build ellipsoids in somewhere. Because you can... So you're saying, or if not, you'd unpack it from... So I could unpack it, take the maximum. It should be fine. We'll lose a bit of precision though, but it should be alright. And it might be a bit slower because all the packing and unpacking. But it saves me allocating more memory. Yeah, something we could play about with later. Let's just get on with it. So you go over all the children, and your main idea is to get the ellipsoid here. So what you want to produce. We'll just call it, I guess we'll call it ellipsoid. So the main idea is you want to produce the biggest, baddest ellipsoid that represents this parent node. Is that true? No, you don't want to do that yet. You want to look at... You go over all the children. And you look over all of their children and find the biggest ellipsoid. So you get all the ellipsoids and find an ellipsoid which covers all of their ellipsoids. Yeah, that's not too difficult. You always say, worry about performance layer. Yeah, it's true to some degree, right? You always want to make sure that the code you write, you've not screwed yourself over later to optimize it. But yeah, you're right in terms of not overly fussing about performance when it comes to thinking about stuff that you're not absolutely sure about, right? Like, sometimes you've just got to run it and see how it behaves and then optimize it from there. But yeah, you should definitely have it set up in a place where you can where you know it needs tweaking, but it can be optimized from there, basically. Yeah, whenever customers have performance, they get frustrated and never write anything. Yeah, it does take a bit long sometimes, but things have to be thought about up front. A design can be counter performance, and you want to try and produce something that's not counter performant, because as soon as you do that, you're just gonna have to rewrite the whole system and all the usage code. Maybe even redesign the whole thing. So you're going over all the children, right? So if we go over all of the children, and then each child, is this the best way to do it? So the parent is going to get to a place. See, this just feels so counterproductive, right? We've had multiple threads visit the parent and say, hey, I'm here, and then they just terminate. Why don't they build their ellipsoid, put it in a place and go, hey, I've been here, right? That makes a lot more sense. So how does one... So yeah, that's really what you want, right? But you got to put it in a place where the parent could just read it from, and then quantize it down into a node again. Because you need to go up to the parent. The parent's then going to allocate 4 children nodes. Or maybe you could say, or maybe you don't have to put it in a temporary place. Maybe instead you do the visit count add. If I'm the first one to reach here, I will allocate the place where it goes. I will allocate the place where it goes. If my visit count equals 0, I'm the one that allocates it. Then what about the rest of the guys that get here? Like, how are we going to keep them in sync? Like, and also, where is it going to get it from? Yeah, so you want to store it. Do you want to store it in the build node? Oh yeah, awesome. Yeah, I've just seen too many things which are too complicated and yeah, unoptimizable. But that's cool. I don't know where I want to stick. Do I stick it? I think I'd just stick it back in the build node. See, I could stick it in the parent of the build node, and then the problem is I don't want to put a spin weight. It just feels odd. Because all the siblings could have come from different directions. But yeah, the C should carry on at this point. Maybe it won't though. But yeah, you'd want to like bump allocate. Say if I bump allocate this here. And then I gotta put it somewhere, so maybe I'd store it in this build node. Like, hey, this is where they go. And maybe it's initialized like U32 max. And then here's where we do that for loop over all those ellipsoids. And then produce the bigger ellipsoid, and then we get the destination index and store our Right, I'm just gonna take a quick break because I'm getting a bit warm and I want to get another drink. And then we'll come back and investigate this. Alright, welcome back everybody. Visit count. Yeah, so if I do something here where I allocate the 4 sets of nodes. Right, I know how to circumvent this problem. We already walk the tree. We already walk the tree when we build the quad tree on the GPU in a build node form. So we already. Oh no, we don't, because there could be a point. Yeah, because they'll get copied out, isn't it? So I could the other way is we quickly walk the tree and then reallocate it all. Because the issue is when we build the quad tree is it could go up another parent and then realize it can fit another node on, and then it just, that previous allocation is now. Wait, that only happens when it's a 3. Wait, let's get something up. So when you're joining a 2 with another, there's only when it's a binary tree. But yes, you have 2 and you have a 1. Then that would allocate a quad node. Yeah, we could allocate the quad node there. And then you'd end up putting another 1 on it. And then you'll just reuse it, and the 1 would be a leaf node. Yeah, it's possible. It's possible. Yeah. But you'd have to put the logic in it. But we could pre-allocate it from before, and then this could be made a lot simpler. So, right, so this code does the same thing where it walks up from the bottom of the tree. It figures out the number of, it gets the left and right node. But yeah, this time it walks up a binary tree from the leaf nodes, and then tries to look at the left and look at the right and sees if it, how many children left and right have, basically the number of grandchildren it has, and sees if it can get rid of the direct child and then join the grandchildren in as the new children. So we just got to be careful. So if it's between 3 and 4, so if it's between 3 and 4 children, this is when it's a candidate to bump allocate. No. Oh yeah, sorry. Yeah, this one is a candidate to B3 to do this bump allocate thing, right? So we should probably get the field in there. So this field will be known as the destination node index. So this is the final. Right, the final node index for packing shader, or is it pack? Yeah, so obviously we only want to do this. So if the node, if the total number of grandchildren is 3 on the left, so yeah, if the children, yeah, so if one of them has a 3, we'll reuse it. So if left is a 3, we'll reuse it. If the right is a 3, we'll reuse that. If not, we allocate ourselves 1. And that should be the logic. So we'll call this destination node index. Right. This would be in the else where we bump allocate it. And maybe there's another else if where we say if the node is the parent, the node index is 0. If it's the root node, then the destination node index is 0 because we've pre-allocated the front so for the root node's children just to go there, and we're getting rid of the root node itself, which is cool. So that would then mean we can get a bit of reuse here. You already would have allocated it. Yeah. So that would then mean you would simply reach into build nodes left node index dot dst node index, and then that would mean you reach into the right, and then obviously to get it all to come full circle, you would simply store. So you would then also need to clear this one to make it an invalid one. Ooh, no, you wouldn't, because you'd never. Yeah, you would never link it back to it. It would never be linked to. The child links are destroyed. But anyway, you would basically like do something like this, right? Voila. Right, that's good. But we obviously got to make sure that we clear the so when we set up the binary tree, we just got to make sure that we actually, set that DST node index. Do we have to make sure? Destination node index. It's always going to be, everything's going to be set that's correct. You hit the leaf nodes. Every parent you go up to that will have. But some will have 2. That's a bit of a funny one, I think. We might not be able to do it. Some of the nodes are going to have 2, and you're not going to be able to join. So I think in those cases, you have to create the destination node index for... Yeah, so before we run... Oh, this would be a bit of fun. We're going to instead print out... So what we can do is we can print out everything and make sure that when we traverse the tree, they always have a destination node index. It could be a bit of a safeguard, to be honest. We can have a bit of a safeguard. It's no worries. We could say, right, if... So when we're trying to use it, DST node index, right? We can just go, well, if it's equal to U32 max, then we didn't actually allocate one. And we can do a return and print out the fact that we encountered this. Whoops. What, build node what? Build node index. Yeah. And then we'll do a return. So we won't get any issues when it comes to memory accesses and things like that. And we can monkey around with the data a bit and see if, do it a few times, and if we don't encounter this anymore, we'll just delete this if statement and voila. Or maybe we could keep it in with a debug check, but yeah. Yeah, so I think there's a case which we haven't handled, but it's good steps. So there's the U32 max being set initially. So I think the case is if you have a binary node. Perry boy, how you doing? How's it going, sir? Good to see you. How you been? So if when you join the 2 children nodes, so you want to save your left node or your right node. Because sometimes you can't join them. I think if I run the here's the case, right? There's a couple of 2s there, a couple of 2s here. You've not been able to join it because there's simply been too many to the left or right. Sorry, Yeah, too many to join between two what would they be called? So that'd be binary tree. Binary tree. Yeah, two cousins, if you will. Yeah, there's too many on too many cousins, right? Or grandchildren from the parents' perspective. So you got too many grandchildren, which would then mean so it'd be an else if branch. Else if you have more grandchildren than 4, then you need to look at the left and right node and be like, oh, you guys, you need to look at the left and right. If they have 2, yeah, so take this. If the left has 2 grandchildren, or the right has 2 grandchildren. So if the left has 2 children, the right has 2 children, you need to do an allocation there for them. Give me, I'm over in the US at the moment. Oh, interesting. You you going there for a little holiday, and whereabouts you visiting? Yeah, I'm doing good, doing good. I've been a bit tired lately, not gonna lie. But yeah, things are great. Um, yeah, the boy is 11 months old now, and he's just started crawling about a week ago. He's been doing that and having a lot of fun. And he started crawling around in his bed and not going to sleep, so it's got a bit of a later bedtime now, by about half an hour. And he's also just started saying no. So he goes like, no, points his finger. So yeah, and he knows when to say it as well. It's a long story, but I met a girl, so came over here for a couple of weeks. Awesome, congratulations, that's great, man. I'm happy for you. Amazing. Yeah, very quick. I don't know if someone handles graphics programming and parenting. Uh, I don't know. They're just fun, man. Like you can just be the ultimate child with your child. It's pretty great, you know. Um, yeah, they laugh, silly, and yeah, it's amazing. Yeah, it doesn't take that many lines of code. They have to handcraft. It's already been crafted for me. Hey, cat. Yeah, yeah. We talk about like you know like I work from home thankfully, so I can be here more for him. So I can take him to his grandparents for daycare in the morning, and I can feed him in the morning, and yeah, I take the morning duty. Um, And yeah, what's great is he goes to bed, and I get to do this, and my wife gets to go to the gym. So we still got our things we can do, and he stays here on the monitor with me. So any issues, which there is none usually, it's all good. But yeah, it'd be hard mode when there's two, but that's what it's like. Yeah. Yeah, rubber duck developing, yeah. Yeah. Well, he can't hear me. Well, maybe he can hear me. Yeah, I think a rubber duck debug with you guys. Sometimes you guys come up with decent ideas. Huh. Second on the way, maybe. We're trying to we're trying to yeah, we're trying to have a baby, whatever that means. Always makes me die when people say we're trying to have a baby. It's just like, so you're, you know, yeah, we're trying hard. um, yeah, trying real hard. We're yeah. Hmm. Will his first words be void main? Yeah, they got to know the arguments in the right order, right? It's in arg c, char star star arg v. You know, they got to know that. That's the second words. Yeah, Perry, we're trying hard. Um, so yeah. What am I even trying to figure out now? Oh yeah. So the problem is with this code is it wouldn't work with the root node, right? Or the root, as some Americans would call it, the root node. Um, so if you have the root node, um, and you're checking how many children does it have. If the children, the left children is, see that this naming just sucks because I've called it grandchildren, but it's not really grandchildren. It's left node's children. No, but it's left grandchildren from the perspective of our current node. Yeah. If it works. Um. So when you have this node, look at the left. What is its children? Well, it's got 4, right? But I'm not gonna. This one is never gonna get it. So when you reach here, only one thread will ever reach here and fail. So that would mean this would do one last check. And then if those ones are, if this one is 2, no, but it always gets allocated. Oh, yeah. We never, the root node is never handled anyway. So the root node always needs to just get 2 seconds. root nodes children go at the start of the allocation. Kabam. Right, I think that's it. So, why don't we wire up that pack quad tree? We've not really done it yet, but we've at least... Oh no, one more. Okay. Right, let's come back here and get it into a good place. So we've gone up from the root nodes. Sorry, the leaf nodes traversing up the tree. And we want to get for every node, we want to get the ellipsoid and create a node. Yeah, pack the node, then go up to the parent. So actually it works a bit differently to the previous one. Let's just figure out how this works. Yeah, so this visit stuff kind of goes at the end. Right, so let's go down from the top. So right, so we get that destination node index. If that is equal to E30 max, we didn't allocate it properly in the previous shader, so we'll return and print out, and we'll know. We can check the terminal for that. Okay. So the next thing to do is say if this is a leaf node, we need to extract the ellipsoid from someplace else. So I guess we say if, how do we figure out if it's a leaf node? Build node index. If it's greater than the build internal nodes, count is leaf node. Then we are simply going to extract, so we want to get the ellipsoid index from the ellipsoid indices. I've got to get that. BVH build ellipsoid indices using the leaf index. Now I get the ellipsoid index, we can extract out the ellipsoid. There we go. So the else statement would be that we need to search over all of the children that have already been packed into the BVH node, unpack the ellipsoids, and then find the new ellipsoid which wraps around all of those ellipsoids, which shouldn't be that hard to do, because something to take note is our ellipsoids don't have to be so our ellipsoids can be rotated, but to make life easier, our bounding ellipsoids will always be upright, because I don't know how I'm going to do all the rotation code, to be honest. It could be possible, but it seems like it's an infinite problem to solve. But maybe there's some smart way you could do it. I don't know. So effectively, we're always going to produce upright ellipsoids with zero rotation for the non-leaf nodes. So it should be quite simple. So you're gonna, so how are we gonna do that again? So I guess let's go over and fish all the ellipsoids out, and then we'll figure it out, right? So we'll get the ellipsoid, and yeah, I've done this because I don't know how I'm gonna, what I'm gonna write afterwards, but let's just, so here we need to look at we need to get the node data. Plus what? Is it destination node index? No, you need to get the children. Shoot, this needs to go up to the parent first. Do I have a parent? Right, you need to get your parent's destination node index. So, but the root node isn't going to have a parent. So you want to say, well, this is not the root node. Yeah, root node is at 0. So while this is not the root node, then we can get the parent. Alright. So this is your parent's destination node index. This is where they're going to go. Something like that, at least. So here we need to fish out the, so for this node, we need to get like the node index for build nodes. This name also sucks. Let's build parent node index. Right, so with the node index, I'm going to say plus child index. Alright. Get in places. So with this, we have not extracted the ellipsoid. What we have done is extracted the, well, we've targeted the BVH node. So there's a way to pull out the center position, schnorm, with this boy, which we made earlier. And there's also a way to pull out the half dimensions unorm, like that, which we made earlier. So we're going to say ellipsoid dot center position, and then say ellipsoid dot half dims. Rightio. So our idea is to build a BVH which wraps. Wait a minute, we need the. Oh, did we not do any rotation? Whoops. I missed that one. So can I so we want to do identity, right? There we go. Nice. So we need to, so in terms of the, so ellipsoid dot rotation is equal to BVH node, ellipsoid rotation, and put all this stuff in. Right, so effectively what we would need to do is construct a bigger ellipsoid from the smaller ones. So let's draw how we're going to do that. So basically, you can imagine you have your ellipsoid. We'll just draw it as an ellipse. So you have a center position, you have a half dims, right? So the idea is we need to get that coordinate. And so that's it at 180 degrees. Is it? Oh, 90 degrees, sorry. No. Yeah, maybe let's look at one a bit more slanted. So yeah, you get your sort of like half dim. Problem with drawings is the drawings are always slightly wrong, and maybe wrong enough. So I don't know. See if your half dims on it. Right. I want to produce another ellipsoid where it represents. So it has no. This one will have no rotation. So I think we just need to get the furthest point. See, if I did center position plus half dims, I've got a point in local space. And then I probably need to apply the rotation or something like that. So I think the rotation stuff will always, yeah, it's untestable right now. So all of our stuff is going to be upright. So when we do the rotation, we've got to build a smaller model and have a bit of a play. But yeah, we can add, the rotation can definitely be added in. This will just have to be monkeyed about with. But I think the logic is, right, we want to produce a new, better ellipsoid. I guess we'll put it here. So this would be the child, we'll call it the child ellipsoid. And the idea is you would produce a, so you produce a point in space, which would then be center position plus the half. Is it plus the half dims? So you rotate, do you rotate the half dims? You rotate the half dims and apply that, something like that. So you do like a, then your rotated offset would be quaternion, I forget my, it's not an OS, is it? OS? What? I put a quad type in the OS. Right, that's for the ages ago and did the controller input stuff to get the right, whoops. Anyway, yeah, so mol quad. Mol V. Bingo. Quaternion. So child ellipsoid rotation, followed by the child ellipsoid half dims. So that thing will get rotated. This could be wrong, but it's okay. We know where to look if it's wrong. And then when you'll produce that point, wait, that's just a new half dims. Maybe that's all you need. Yes, you max it. Yeah, you probably produce a max and a min point in 3D space. So your min max, and then from there you could figure out the half dim. Is that right? I think that's right. So that'd be like a positive infinity. Negative infinity. Don't know about that. Yeah. So you would then do min equals the minimum between so it'd be the sub of PT with offset. So obviously it's min in there. And then max is the same, just replace with max. And then an add. So I think that will then produce you an actual ellipsoid. So you want to set ellipsoid dot center position. So that's the average of the min max. So you could just add the two together, divide by 2, or you take the difference. Take the difference and half it, because you're gonna have to do that anyway. So it'd be like half dims equals sub max take min, and then do a moles. So half it, right? And then you can do a to produce the center position. It is simply adding the min with the half dims, and you'll end up at the center. And then obviously the rotation, we are just going to do a quaternion identity. Right, so that is how you would produce a parent node with an ellipsoid, which is that encompasses all the children ellipsoids. It should work. We'll see. So if you are a leaf node, though, you just fetch out the ellipsoid from the build ellipsoids array. Right, so after we've got this, we then need to pack it back into an actual node and then store it in this BVH nodes array. So what we need to do is basically do something like so. Oh wait, I realize it's going to have a material in there as well. Yeah, some of the stuff we don't actually need. I think this is dumb doing it this way. This is only needed for. Yeah, we can put them out manually. That's okay. Right. Well, so I think this needs. So we need to have the half dims. Because the problem is there's that material index. Where's the inputs for that? It's this one here. BVH node in it. Right, so this is what we've got to get to. So we've got to build a BVH node. So we need that node type. So either it's the leaf node or it's a parent node. So that's we can easily work that out. Then we need the center position norm. And then we need the half dims unorm. Then we also need the rotation, which is going to be basically nothing for one of them. And then we need that U32 reference index, which is a material index for the leaf node and is a child node start indices. Yes. Easy. Right, so let's change that around. So we get the ellipsoid, and we're literally just going to unpack it into these locals. Snorm equals ellipsoid snorm. Center position, sorry. Then this is half dims. Then the other one is rotation. Then the final one is ref index, ellipsoid, material index. And there we go. So that is if it's a leaf node. Then if it's a non-leaf node, we want to, oh yeah, we need the type. Type is equal to BVH node type. Bottom level leaf for now because I don't have a top level yet. Awesome. So how do we do this here? Well, we do something like this. Then rotation is just dropping that like that. What about the ref index? So this one needs to be whatever the parent. It's this thing here. Build node parent, destination node index. Is that right? So we need to be able to, so we're a leaf node. Yeah, we're saying we are a parent. Is that right? Type equal BVH node type parent. And then we're going to store that node in here. There's the node type. Excuse me. Right, so are we getting this right? So we need to find in our parent node, we need to find which child we are in the parent node. So there needs to be a bit of code here. So this doesn't need to do. Oh yeah, we do. We need that. Destination node index, we needed that. So we need to go over all the children in the parent and figure out which child we are. So that can happen here. So child index. So we go over all the children. Where's the children at? Children count. Where's that? I thought I saw that in a local somewhere, but obviously not. But yeah, for this node, how many children does it have? So you need to do the same thing, but for the parent. So you need to figure out how many you want to know your sibling index, I guess is the word. So you'll go to the parent, get the number of siblings. So that's build parent node index. Let's call it sib index for short. And you're trying to find when the build nodes children indices. Get that music back. Sib index is equal, right, to build node index. Get Stone Rebel back. Right, so when we've found which, so I guess we could probably remove this and just have it cached because it's just a 2-bit value that we need. But yeah, stuff we can play about with when we're optimizing in the future. Yeah, so sibling index equals sib index, then we break. All right. So now that we have that, we have everything we need to put that node in. So sibling index, and you poke that all in there like that, and so I think we're very close. We just got to go up to the parent now. So you go to the, so you probably say up the visit count in the parent, right? And then you're saying how many children does the parent have if the visit count is not equal to number of children take 1, I think it is, then yeah, don't traverse up the tree basically anymore and stop. So only the final child to reach the parent is allowed to carry on, and then that means that none of the siblings or the descendants will be accessing, no threads will be accessing those nodes. So you should be able to just keep going around and there'll be no problems. Let's quickly revisit that. Well, let's get compiling first. And then we'll revisit it. There's no else statement though, is there? Alright, what's this saying? Did I spell ellipsoid wrong a few times? Ellipsoid, whoops. Ellipsoid. What is this spelling? Ellipsoid. Wow. It is everywhere. No. Alright, it's good. I think we're back in business. So let's get that compiling. What is that one saying? No what? No infinity. Oh, you F32. Yeah, I did that. Right. So the thing we're building now, so we're going to double check, make sure the shader is A-OK, then we're going to launch it and hold on tight. So we dispatch over all the leaf nodes. The number of build internal nodes is that tick 1, which is for a binary tree, but we turn our binary tree into a quad tree and it stays in the same allocation, so that's the number of nodes it uses. Our node index is the number of internal nodes plus this leaf node index. That'll be our node index for the leaf node, while it's not the root node. Whoops, what is all this nonsense? Parent node is equal to build node parent index. Destination node indexes should be set. If it's not set, return and complaint. These would all be set in these two if statements. If it is a leaf node, get the ellipsoid index. Yep. Then get the ellipsoid. Extract out the ellipsoid into these lovely local variables. Then if it's not a leaf node, go over all of the children nodes and extract out the ellipsoid and compute the bounding ellipsoid. Where do the nodes live? How many children do they have? Go over all the children. Extract out, yes. Point, apply the rotation. Then apply the rotation. Sub for min, add for max. Yep. Then take the min max. Then that's parent, yep. Sub the min max, take the difference in the min max, half it, that's the half dims. Then add from the min and produce. Yep. So sibling index, siblings count. So go up to the parent, get the number of children, that's the siblings, find your node. Hopefully we can move that in the future. Then we assign our node in here. Right. That's all correct. Go up to the parent, up the visit count. If we're the last node to visit, if we're not the last node to visit, return. If we're the last node to visit, carry on up the tree. All right, looking good. So let's go ahead and launch this thing and cross our fingers and see if it works. So we are going to then pack the quad tree. So to pack the quad tree, that is going to be all of these boys and girls. So we've got the build nodes, we've got the final destination nodes. We also have the ellipsoid indices. And then we also have the ellipsoids themselves. And then we also have the node start index, which is just going to be 0 to do allocate. And maybe this comes from, it's either CPU side allocated or GPU side. Maybe it could just be CPU because it's probably not going to be too crazy. Yeah, buffer ID. Crying out loud. Right, build ellipsoids. Ooh. Right, they're not got the build in there. Bit of an inconsistency, but that's the way it is. Alright. So, the next thing we need is synchronization code, and then we can launch it. So, read write on the build nodes, and then we want read only on the ellipsoid buffers. And how many of these boys and girls are we launching? Well, we need to launch as many as there are leaf nodes, and that is simply ellipsoids count, right? Okay, so let's press F5, give that a lovely compile, and let's see how this goes. So if the stream dies, I'll be right back. Hopefully it doesn't though. Right, so it seems to have worked, and what I don't see is any printing, but I could be wrong. So what I'm going to do is I'm going to, you see here, I'm going to say or1 and just let it print out that oops thing and just see what happens. Nothing. Clear problemo. So we're not knowing if why aren't I seeing this? That's clearly equal to summon. Damn it, I launched the wrong shader. I didn't change the shader that I was launching. That could have ended badly, but it didn't. Right, so apparently it's running it now. I'm not seeing any other prints. So I'm going to go ahead and do that same thing that I tried to do a second ago, where I'm going to OR the 1 on here and just let it always print. Right there. Oh, so we're seeing it. Oh. Obviously only happens on the first one of the first frames, doesn't it? So we'll right, let's run it, then kill it. Okay, so we are seeing it print out. Damn it. So the shader's not running successfully. Some of the nodes haven't got the destination node index allocated. And I was hoping that we caught all of those. But we haven't. So there's certain cases where that doesn't happen. So we can try and visualize the tree on CPU and then see that. So if we visualize it on CPU, we might be able to understand the problem better. So there's an ellipsoid array. Excuse me. So we're doing a bunch of random things. So why don't we take this and then move this up above all this debug drawing for the thing. And what we can do is bring this ellipsoids. So there's the srand. So it should be deterministic, right? Predictable. Then what I would like to do is make it such that we see this tree on the screen. So I need to probably take this sort of code here. So there's more codes, right? A number of leaves and all this stuff. I'm gonna comment out what do I need to do? I need to store them in here. Yeah, so leaf more codes. That one needs this thing here. Right, so plop that in there like that. So we're copying them from those hard-coded ellipsoids. Well, no, hard-coded randomness ellipsoids. And then we just need to put the numbers in. 128. And if I drag it over, it might be a bit buggy, but there we go. Right, so see how that works. Got a segfault. It shouldn't segfault like that. It should give me a stack trace. Ah. Oh, we only went up to 64 nodes. Right, let's take this number down a bit. Right, I think we only went up to 64. That's cool. Alright. I've forgotten what happened here. Oh, we could try 32. Still though. What's the problem? So we're doing... So that's, I think it's when we try and quantify it. So let's just get the binary tree one working. That's the only one we need to work, but still. I don't want it. Alright, this one still fails. Wonder why. Oh. Oh, have we got overlapping? Yeah, we haven't even got the uniqueifier shader, isn't it? So we're getting recursive descent. Or sorry, yeah, we're getting infinitely recursive descent. So that would then mean we quickly need to run a thing that uniqueifies these, right? So it's all right. We can do that. We just go over all of them again. You check where your last one, and so you start from 1. You check with the one before. Previous. So we wrote a GPU version of this, which does it in a highly parallel way. But this is for our CPU test code. So I'm just doing the same thing again, but it's far simpler, obviously. And we make sure that our current one is equal to the maximum between this plus 1 and myself. I'll do it. Right, so if your previous one is 128, you go, the next one has to be 129 or above. And that's how the GPU code works, but it does it in a highly parallel way. Right, here we go. We're getting a result. This is what we get apparently. So, and we could check that. We could verify it. Why is that not got a Morton code? Sounds a bit fishy there. Why is that not got a Morton code? Yeah, this might be a bit wrong. So we open up RenderDoc, we can find out. So we can see the buffer in which it is. So I take a screenshot, and then if I... Sorry, that's done another capture, isn't it? I might have done a screenshot as well in my game. Let me find out. Just my screenshot button. Yeah, I did a screenshot too. There we go. So if we open up one of the first capture, it has to be the first one. And what we find out is we're looking for the quad tree one, isn't it? Build quad tree is our boy. Here's our data. Here's our format. All right. So it points to what? Why is the physics count so high? Oh, it wouldn't have got reset, maybe? But anyway. Right, that looks like a load of crap. Oh no, we changed the format. Whoops. I don't know why it's a load of crap. We added a destination node index. I've got to save a new one. For crying out loud. I've been that. Right. These look a bit better. Bit. Why is that 3? Yeah, so clearly they're not the same. That ain't good. Right, let me look at that. CPU side code, it just feels wrong. Right, so the ellipsoids have been made. They set the internal nodes to 0 for the Morton code. The leaf node Morton codes get set up correctly by the looks of it. Then deduplicate. Yeah. Sort. Then go over all of the leaf nodes and set them on code in there after being sorted. So why does it look wrong? What did I change? I used to have it mean, this used to say like rand, right? So if I just do that, it's ellipsis count maybe. Right, that seems alright. I think. Let's change something else. Change the seed a bit on that one. Right, seems alright too. Let me take a look at the I think it must be between 0 and 1. Maybe it's not. Right, these look alright. But the fact that we produced an invalid looking thing was not good. We should output all the Morton codes and see what it's saying. Right, let's undo that and get back to here because it looks like we didn't do anything wrong. Let's output the Morton codes. What? Let's see what we get. Right, so apparently there's duplicates. Well, there's a bunch of zeros. That definitely looks a bit fishy. Let's change the seed. Still a bunch of zeros in there. Zero's a bit fishy though. So let's punch in there the coordinates. See what's up there. Well, that looked planned. Clearly it's all over the place. We should pad the ints at least. If you pad the ints by pad them with like 20. Maybe it's way too many. Yeah, I think it's way too many, but still, who cares? Right. It's a bit better. Got some negatives in there. Yeah, the zeros are not duplicates. Oh, there's a negative value. Yeah, we shouldn't have negative values, right? So that's the problem. We've got big negative values. So, oh yeah. Oh wait, what do I mean? Oh yeah. Times 2? This is norm. It needs to be unorm. This is times 0.5 plus u 0.5. Whoopsie. Alright. I think we found ourselves a bug. Okay, so clearly, big old problem there. So that was messing up our GPU one as well, probably. So, okay, let's run that. That looks better. I'm just questioning about the, did I accidentally... No, that's the right seed, isn't it? Double check that. Right, we didn't change the seed. That's cool. Right, so I'm just going to go ahead now and put that print back in. I just want to see the values, make sure they're all good. For some reason I removed it. Still negative. What? So what are they? Oh yeah, sorry. Yeah, they're negative, and then I turn it into a positive value. Sorry, a 0 to 1 value. Right. Okay, that's good. That's good. That's good. So then they produce proper codes. Excellent. Rightio. Rightio. So now we can. So remember, there was that printing that was supposedly going on the first frame. Is it still happening now? Yeah, it still happens. So we've still got to investigate it. But now we've got a debug visualization on the screen. So all we have to do is open up the game. We take a screenshot. So here's our node graph here. It could be a bit wider, to be honest, because I can't see half of those guys. But could we cheese it a bit? There's a thing somewhere. See, I wonder if you change that to 2, does it render them all? No, it messes the whole thing up. Yeah, so there's a draw, and like it takes the children capacity in. So if you divide that by 2 instead, that might make it better. Nah, it's divided by 3 instead. Crap, did we just see it link? Am I seeing multiple references to the same nodes? Something's wrong. Right, okay, that was right, that's because it was drawing the nodes on top of each other because that divide by. Okay. Yeah, so perhaps what we'll do is we'll reduce the number of nodes just so we can create a smaller example that we can actually manage to debug. So let's make this 16 and hopefully we encounter the problem. Right, so there's a couple of boys and girls here, 18 and 19. Where are they? 18. 18. That's a leaf node. I guess 19 is a leaf node as well, right? I can't see it, so it must be that one there. 19, 20, 21, 22, 23, right? So they're leaf nodes. That's illegal. So basically, I think the checking logic in the shader should only be doing this if it is not a leaf node, right? If is less than. Oh, wait. It's using the parents one. So yeah, it's not, the parent is not a leaf node, obviously. Yeah, same for the parent of 18 and 19. What happened to my numbers? The parent, so it's 3. This guy doesn't have a, this one doesn't have it. So that's, and then 19, so that one doesn't have it either. So this one is the child of the root node. Yeah, remember we did that logic, and I think I messed it up. Yeah, I have to go over the... to the parent... So what did the tree look like before this? How did it turn into that? There's a binary tree version. Let's enable that, we'll see it. So that left-hand side... Right, here it is. So there's that 3 node. 18 and 17. So 2 gets cut out. These 2 join into 3 nodes. Right, so that'll produce a 3. And then 1 would be the one with the destination node index. Right? Then... yeah, the logic is here. The logic is literally here. It's all... So we say... the first one we'll call this line. And it'll do that. Hey, I'm new around here. Do you mind answering a few questions about NeoVim? Or is this not a good time? I'm not really much of a good person to ask about NeoVim because... yeah, I just set it up and then use it. I'm not much of a master at NeoVim, basically. I don't know much about it. I kind of just set it and forget it, you know. So, but if you ask the questions in the chat, someone else might be able to help you out. Because there's quite a lot of people who are into NeoVim on Twitch. If you cut this node, you join these. Yeah, so that should get... if the total grandchildren is 3 or more, yeah, it should allocate that. This will then get set down here for this node. Yes. Wait, for which node? This one. Yeah, we'll get the... Sweet. So that should get it. And then the right-hand side... If the right-hand side is equal to 3, or the left-hand side is equal to 3, and you're joining them, so this will have 3, this one will have this one, this one, and this one. The same thing will happen again. It's got a left-hand side with 1. The total number is between 3 and 4. Comes in tiers. The left got 3? No. Has the right got 3? Yes. So 1 will then get axed. And then it should copy it from there. But might have to do an atomic. Is it just missing an atomic? Because it's caches and stuff, right? Because you're... Yeah, I think it's missing an atomic. I think that's right. Crying out loud. E32. That should be it. 18 and 19 are still failing. So I could say, well, if you've got... It's a parent of 3, isn't it? I can follow it. Like, what does it do? If your parent is index 3, I can just be like, well, what are these things? Grandchildren count, so this equal this plus this, so left plus right. Left, right, grandchildren. So we should be able to see those there, which would be super sweet. I'm just considering to switch, so no advanced questions, just how long you've been using it and how it's experience for you. Is there a reason to use HJK instead of the arrow keys? You can use the arrow keys, they work. I've changed mine from HJK to the right by 1 to where your hands rest naturally on the keyboard. So you're not moving to the left and moving to the right, because that's just like basically the thing you'll take away from Vim is built for an older PC. Like, it was built for a very specific PC, and some things in it just don't make sense. So you sometimes have, like, Vim is about configuring it basically. Some people don't configure it, and they just use default Vim. But NeoVim is definitely built to be configured heavily. But yeah, the HJK thing, you'll get used to it, it's alright. And then you don't have to move your hands much. You can still use the arrow keys. The problem with using the arrow keys is Vim has a bunch of combination keys. And when you use the combination keys with the arrow keys, it'll be a bit weird, I think. It'll be less smooth. Is there no node that's equal to 3? What the what? equals 1 plus 1. What? Do I need atomics in there as well? Because this was working fine. Like, okay, so if I look at that tree. It's saying 1 plus... Right, let's also debug print out 2 and 1. You don't know which is which though, so you gotta do this. I see, by the way, I used to interact with the file system inside the editor. How do I do that in Vim? What do you mean by interact with the file system? You mean have a side panel with like a tree view? Does that mean interact with the file system? Because you can also get... Because people just use a terminal window sometimes. If they want to actually interact with it, as in edit, navigate and stuff. Or run commands in the file system. Rest 2. Add 2 to the right. This just feels weird. 2 add 2 to the right? What? 2 add 2 to the right? Two had 2 to the right. Huh? You go up to the parent. One not equal to invalid. Hey. Yeah, it's been great. Good time. Yeah. That panel just over the studio. Right. Yeah, you can. There's plugins for that. I don't think you also need plugins as well. There's ways to do it without plugins, I think. Yeah, there's plugins for it. But there's much better plugins. Like, there's what, so you can have full screen for code and you don't need to have stuff like that, so you can fuzzy search for things. I think there's TJ's Telescope, which is very popular in NeoVim. I had it and then I broke it. But yeah, you can like set it to like, if you press the spacebar or something, and you can just start searching for files or searching for, you can grep in it. So you can search via file names, you can grep in files. There's a whole bunch of things you could do with it. Pretty good. So when you have stuff like this, you sometimes don't need that navigation panel. How are we going to... It's just bizarre. Yeah, I think I need atomics. I think this is my problem. So let me figure out... If I do atomic, like, but why do I need atomics now? When it appears to have worked fine before. Am I missing something? Excuse me. I've seen the one. I'm just not sure how you would create rename files, etc. As they usually don't take much space since they're docked and can be hidden. I don't know. They probably don't take that much space inside Visual Studio, but in a terminal layout, they're going to take up as many. They could be probably quite wide, to be honest. I'm quite zoomed in here, but yeah, they could probably be much wider than they would be because the whole terminal has a fixed font size, right? Um, yeah, they'll take up more space inside terminal. Right, still got the same outputs. Right, maybe the data that we're looking at is different. I didn't actually check that. Let me undo some of this stuff. I didn't actually check if the linked thing is the same. So we should check that quick. Alright, I got that screenshot. Render dark. Done the capture first frame. So I can inspect the tree that it builds. That's the pack. This one's the build nodes for the quad tree. Right, this looks like it. Right, so 0 should link to 3, so links to 4 and 5. And has 4 children. Right, we're looking at different trees. Damn it. Why are we looking at different trees? What did I do? Right, so we'll undo this, where we added the atomics. It might not be needed. So yeah, why are the trees different? Are they like what did we do? Could it be that the sorting algorithm is a bit... No, there's no duplicates. Yes, the sorting algorithm would be the same output. We can compare the two more code outputs maybe. So we took a dump of that there, and we rerun. Wait, we already have the molten code output. I didn't change anything. So I just go back. Molten code, uniqueified buffer. Is it already unique? Probably. I don't know. Should be alright. Is this before it's sorted? Yeah, we want to view it after it's sorted actually. Whoops. Where's after it's sorted? It's here, isn't it? Let me copy that. These are different values. Also, why isn't this just a U32? So silly. Right, what's going on here? Right, that 631 is in there. Am I missing the first one? Oh. This is a bit strange. I think that uniqueify function that runs is messing things up a bit. Yeah, right, this uniqueify thing that I wrote is wrong. It really is messing things up. So this needs to run after the sorting. Crap. That's the reason why they're not in sync probably. So if we run that, they should be in sync now. Right, this looks better. Right, 2 whatever 90, yeah. 63, that's right. 809. Yeah. Right. Yeah, those look good now. There's about 15 of them. Yeah, they're looking good. So yeah, chat just typically pretty quiet, which is cool. Huh. So we should have the correct tree now. Right, we should have the correct tree. So it was the parent of 18 and 19, I think, which had the bug. Yeah, 18 and 19. The parent of those guys is not being made right, 18, 19. Yeah, 3. Interesting. Right. So that one is when it's a leaf node. So these are two leaf nodes. Is too much. It's too much to join these two together and produce all of these under one node, right? Because our maximum is 4 and this is 5. So I thought I handled that. There's a thing for it. It's here. If the total grandchildren count is more than 4, then bump allocate. Oh crap. Man, oh, so silly. Man, I'm so silly. Can't believe it. This is meant to assign to the right hand side or left hand side node. Man, I had it all thought through fine. Left node index dot destination node index. Right, so that should be bug free now. Yes, so it's not finding a node. So when we're doing the packing code, it's not finding a node where the destination node index was not allocated in the previous shader, which is proper sweet. So I'm just going to increase the number of nodes, make it a more complex tree, and then I'm going to change the seed around a few times and see if we encounter the problem. So let's make this 64 now, which is the biggest. We'll go with the debugging UI. You just let Henry cook or have him on doing something. Sweet. Yeah, I think most people typically do sort of like programming while I program, and we sort of succeed or suffer together, you know? So this one seems to be produced fine. So I think we've actually packed our nodes successfully. We're not getting any printing there. I want to change the seed though. Yeah, so not getting any of those debug prints anymore, which is great. So let's change the seed. Let's drop a 5 in there. Get a different tree. So this is the tree we're building on the GPU. And crap. 28 and 29. Sorry, 27 and 28. These guys are obviously causing us problems. I can't see 27 or 28 because it's just too... Oh, they're here. Right, so the root node. Why did I not solve this then? So the root node, look at the logic. Why doesn't it do it? So the root node, you visit the root node and it should be the same logic, right? So can I do like a if node index equals 0? Equal that plus that. Right, so we should see the two counts in there and we can hopefully deduce what's going on. So it's saying 2 plus 4. So 2 plus 4 is 6, obviously, right? And the values seem correct. Right, because what 2 on the left here is 4 here, so 6 overall. So we don't go into here and try and join them. Instead we go here. Wait, it's saying the parent of these two. Node 0. It's right here. Oh, of course, node index. Ah, that should set that to 0. That was indexing U32 max. Right. I see the problem. I see the problem. Okay, so hopefully that's fixed it. Yeah, that's good. So the root node now gets its destination node index set up right. So the root node, its children nodes will just start at 0. And we'll get rid of the root node when we pack the quad tree, which would be good. Or we have already done it. That's what's great. So let's do a couple more tests. Let's just change the seed again. And let's just see if the printouts show. Here's a different one. Right, there's no printing there, which says whoops. Sweet. Let's change the value of that. And there's no whoops there either. Right, so I think we're at a place, pretty good place. So we should be, it seems like, let's go to where the pack, right. So it seems like we're building a BVH tree successfully now. into the format that we're ready to ray trace against. So we've got these Morton codes that we're uniquifying. We build the binary tree, we build the quad tree in the sort of temporary build node state, and then we pack the quad tree down into a nice packed tree. So the next step is we want to run the BVH ray tracer, and we want to ray trace against this bottom level BVH which we've just built and try and render it in the scene. So unfortunately I'm going to have to start that next time, so that'll be on Thursday at 6:30, 7 p.m, 7:30 p.m GMT +1. But yeah, at least we finally got the tree all packed. That's good. That took a lot longer than I hoped. It was a bit fiddly, but it's good. Yeah. Oh no, it's the visualization for the quad for the BVH. So we've got a custom BVH that we're building to ray trace against a bunch of ellipsoids. So here's one ellipsoid that we're rendering. We are trying to ray trace a bunch of ellipsoids. So we've built a BVH on the GPU, and this is the bounding volume hierarchy. It has at most 4 children, and each node represents an ellipsoid which wraps all of the children nodes, right? So it basically partitions the space with a tree of ellipsoids, and the leaf nodes represents ellipsoids that we're going to render. So how this differs from other BVHs is that it is ellipsoids all the way down, and we render ellipsoids. So yeah, it's all in place now to at least ray trace against. So we'll be starting the ray tracer. It'll test here. Sorry, it'll test all of these children, and then recursively go down the ones that it hits until it hits a leaf, and then it will render that one. So yeah, it's pretty sweet. Because I want to try and build. So I was doing a sphere. I was doing spheres, but the spheres were too limiting. I couldn't shape them in different ways. So we actually just dumped the sphere renderer that we had. So we got PBR as well in. We did that recently. But yeah, I wanna make it so you can construct models out of ellipsoids, and you can rotate them and everything. Boxes are a little bit too sharp on the edges, but maybe that could work as well. The problem with boxes, you end up basically making another voxel renderer, and there's plenty of voxel renderers out there. So I'm trying to just do something that's just a little bit different, and come up with some different art style, if you will. So we're just seeing where this goes, but it should be cool. I think we can make something look good. So yeah, we're just doing something completely different, and we're ray tracing against everything, and I'm going to try and make it so we can anti-alias in the ray tracing as well, hopefully. But yeah, it's going to be sweet. But yeah, if you want to ask any more questions or talk about the project, there is a Discord channel where we talk off stream about stuff. I also have a YouTube and stuff where people can catch up on the project, VOD channel. I'm hoping to post a devlog soon when we have the BVH stuff, the bottom level stuff done for the BVH, so we can at least see something, see a result, and then I can talk about how we got there. Right, so I'm gonna find someone to raid. But yeah, next be on Thursday and Sunday. Take a look at the timelines to find out exactly when. Um, Ginger Bill is streaming. Let's just raid him. All right. No worries. That's cool, man. Yeah, have a good rest of your week, guys. I'll see you Thursday. Catch you later.